Okay. Yeah.
Sick. So Matej, thanks for coming to talk to us. We're really excited about this. I was going to introduce you as coming from Lurk Labs, but I guess that has been rebranded. So now you're at the Argument Computer Corporation, which is like metal as fuck and an incredibly cool sounding name. Um, and we're really excited to have you here. So, thanks for joining us.
Yeah. Thanks for inviting me. So I saw that generally this plan is that there's like a lot of time for question and answer. So I prepared some slides, but I want to get through them kind of as fast as I can so we can get to the interesting stuff. I'll do like a tiny little demo in the middle just to show off, but then I'll leave most of the time for question and answer, I hope.
That sounds great.
Um, yeah, great. So thanks again, Max. So like Max said, I'm coming to you from the Argument Computer Corporation. My slides are down here. I don't know. Can you see my cursor if I move it around?
Yep.
Okay, great. Yeah. So here are my slides. If you want to follow along, just don't spoil anything for your fellow participants. And yeah, so thanks again for the invitation. So I guess I'll just start with who I am. I'm a software engineer and aspiring cryptographer at Argument Computer Corporation. But before this, I was a mathematical physicist. I did my PhD in math at University of Illinois, and I actually did a postdoc at Northeastern. So I spent a good 3 years in Boston. Love the place. Love it when I get to visit again. So yeah, it's good to give a talk to some Bostonites or Bostonians. But that's enough about me. So let's talk about Lurk. So what is Lurk? Lurk is a Lisp. And I'll just end it there. Any questions? Just kidding. So there's more to Lurk than just being a Lisp, but the surface level syntax of the language is that it's a Lisp. But kind of like the semantics of Lurk is via the CEK abstract machine. I'll talk a little bit more about that later, but it has like some concrete semantics that it implements. And sort of the secret sauce about Lurk is that it can provide succinctly verifiable proofs of execution. So the idea is that you'll run a Lurk program and you'll generate some proof, be it zero knowledge proof or non-zero knowledge proof about the execution. And that will be something that you can send to someone else. They can inspect the proof, verify the proof, etc. And the current implementation of Lurk can be found here at this GitHub repository, argument computer /Lurk RS. We have some really cool stuff cooking up at Argument, where a new version of Lurk is about to be released. The performance is a lot better. A lot of like cool, new, interesting cryptography was put into it. It's not public yet, so I'll be focusing on this older version of Lurk. But if you come back to us in like a month, maybe even a couple of weeks, you'll see like some exciting stuff happening. But for now, let's talk about this Lurk stuff that's not under embargo. Um, so let's kind of go through this list kind of one by one and then put it all together at the end again. And we'll kind of see everything that is to Lurk at the very end. So first, Lurk is a Lisp. So it has a fully functional REPL and interpreter implemented in Rust. Here's just like a code snippet. You define S expressions. So here we're defining the Fibonacci function, and you can evaluate the Fibonacci function just as you would any other Lisp type language. And you'll see here there's an additional little information about how many iterations it took to prove something or to evaluate something. That'll be important a little bit later when it comes to proving. But the result of fib of 10 is 55 is kind of what you would expect. So yeah, so Lurk is a Lisp. Lurk is also an implementation of the CEK abstract machine. So what is the CEK machine? I was never a computer scientist, so I don't know how broadly known this kind of stuff is. But it's an abstract model for computation, and it's basically an object. It's an abstract machine that takes in expressions, an environment, and a continuation, and it spits out an expression, environment, and continuation according to some very specific rules. And I took a screenshot from sort of the paper where the CEK machine is described. I have some references at the end if you want to go back into the references. And here you'll see all the various different forms that the CEK reduction can take. So for abstractions, it adds in a return value to the continuation. So it's a return continuation. For a particular application, you'll see that it's a argument continuation. If you go through the paper, all of these different symbols are described and defined, but for now, it's just kind of the semantics of what the language implements. But sort of the main focus I want to talk about is verifiable computation. And so Lurk, not only is it a programming language, but it's a programming language that can prove facts about its execution. So what is verifiable computation? It's kind of most abstractly just a protocol between two parties, a prover and a verifier, where the prover is going to be doing the execution and running the program, and in the same time generating a proof pi of the execution. And then the verifier will receive some subset of inputs and outputs depending on how, whether the proof is expected to be zero knowledge or not. And presumably, if the proof is accurately provided by the prover, then they'll be confident that f of z was computed correctly if they verify that proof. So in practice, what does verifiable computation look like? So sort of the first step in being able to do any verifiable computation is you need to encode your function that you're generating proofs about in some sort of representation that's amenable for generating these proofs. And this step is known as something like making, arithmetizing the calculation, and the different kinds of arithmetizations that are used in practice now. There's a lot of names like R1CS, short for rank 1 constraint systems, AIR, short for algebraic intermediate representation. There's Plonk, which is a particular kind of arithmetization. There's a lot of different arithmetizations that are used, but they're all sort of similar in the sense that they're defined as kind of like, sort of traces of execution defined over some finite field. And the constraints that exist on these traces are generally of the form of polynomial constraints. And I'll give you a few examples in a bit, but that's generally the kinds of things that you would expect from an arithmetization. So you'll take some function that you'll write in whatever higher level syntax that you want and turn it into some big list of polynomials and polynomial constraints that the trace has to satisfy. And it should be said that the resulting circuit, so a lot of times this arithmetized object that you have as a result is called a circuit, and the resulting circuit is so-called flat and unrolled. So unrolled in the sense that anytime there's a loop, you sort of like unroll that loop. So if there's a loop of, say, do this operation 10 times, then you'll take that function, literally unroll it 10 times, and you'll have like a circuit kind of glued onto itself 10 times. And it's flat in the sense that if there's a conditional, like an if then else, then the circuit actually has to do both branches of the if then else computation. And so this is kind of like the first surface level way that you arithmetize things. Just kind of the last thing I want to mention is that the point of generating these proofs is that presumably the work that it takes to verify the proof should be less than the work it takes to compute the result. So in practice, if you want, the succinctness of the proof is generally taken to mean that the proof should be, or the verification cost of the proof should be something like logarithmic in the execution cost. Because I mean, if it was anything like on top of execution cost, then what's the point for the verifier? They could just recompute the function themselves. Kind of delving a little bit deeper into verifiable computation. So the variables that appear in your trace are allocated and constrained with polynomials, like I said before. And the allocation is generally something that can happen non-deterministically by the prover. So for example, if I have a circuit where I just have a single constraint that E times F is equal to 1, say E is my public input, then F, if I'm a prover and I can allocate the variable F appropriately, and I have this constraint that E times F equals 1, then this essentially constrains F to be E inverse. And so instead of in the circuit going through like Euclid's algorithm to like invert finite field elements or whatever, you can just non-deterministically provide F, and then that'll be your inverse. Another example is, say, for example, I want to take D as my input, and I have a constraint that x squared equals D. So this would essentially mean if I'm able to non-deterministically provide x, I'm basically providing a square root of D without any of that extra effort of going through the various algorithms you have to calculate square roots in finite fields. And so non-determinism in constraints is a very interesting paradigm. It adds in a lot of computable, or it adds in a lot of like strength for your computation, but it also adds in a lot of like foot guns that you need to avoid. So under constraining your circuits can generally lead to a lot of security issues. And then over constraining your circuits then, on the other hand, makes the provers work a lot harder. So the number of constraints is generally the metric that you want to use to determine how costly it is for the prover to prove something. So as the number of constraints increases, the number of operations the prover has to do increases, and you want to sort of generally minimize the number of constraints, but at the same time keeping all of the necessary constraints to keep everything, appropriately constrained. And then another example is just to see like a little bit of a hint of like what actual computation could look like. If I have a constraint on a variable b of b times b equals b, then it's essentially constrains b to be a Boolean. So the only solution to this equation over a finite field is for b to be either 0 or 1. And so adding in another constraint, say something like d equals b times a plus 1 minus b times c, if b is appropriately constrained to be a Boolean, then this essentially says that if b is equal to 1, this selects out d to be equal to a, and if b is not equal to 1, if b is 0, then this selects out d to equal c. So setting d equal to this polynomial constraint over on the left-hand side is essentially saying d equals if b, then a, else c. So you can sort of see a little bit of a hint of how you'd implement conditionals. And once you have conditionals and once you have unrolled loops, in some sense, you kind of have some naive form of Turing completeness. So verifiable computations. So I'm going to I have a lot of graphs. And so I want to kind of just schematically give you a sense of what the verifiable computation should look like. So essentially the prover's work here is taking in some input z in, evaluating f, and spitting out a z out. And it's a little hard to see from the slides, but you'll see here that this pi is actually coming out of the prover's work. It's not necessarily coming out of the function itself. So the function isn't the thing that calculates the proof. The prover has to do some extra work on top of the function to calculate that proof. And then on the other hand, the verifier takes in the inputs, the outputs, and the proof, and will spit out a 0 or 1 depending on if they believe the proof or not. And if they believe the proof, then they should be confident that z in or f evaluated on z in equals z out. And if they're not confident, then they shouldn't believe whatever the prover is giving them. And then I've mentioned before, but the protocols, in order to be like a well-used protocol, needs to have a certain set of properties, has to be succinct. So the proofs have to be easily verifiable by the verifier, basically less work than actually recomputing the function yourself. So the protocol has to satisfy completeness. So if f actually did manage to evaluate the function on z in, then they should be able to generate a proof. So there shouldn't be any stumbling blocks. There shouldn't be any NP statements that the prover is not able to prove. Soundness. So soundness is more of a cryptographic assumption. So the proof doesn't necessarily have to be 100% believable. So for example, if I restrict myself to instead of talking about proofs and I talk about arguments, so arguments, there's always a little bit of a cryptographic chance that the prover has done some amazing thing, like finding a preimage to a hash function or calculating the the discrete logarithm of some very difficult cryptographic group. So like if the prover is able to do these kinds of things, then they would be able to make fake arguments that the verifier would believe, even though they wouldn't have actually calculated the function correctly. But assuming the difficulty of collision-resistant hash functions or the discrete logarithm on certain algebraic groups, then soundness is essentially saying that the arguments that are provided by the verifier or that are provided by the prover should be verified. And if they are verified, then the verifier can be very confident that they're actually correct. And then the last property is zero knowledge. So sometimes the input or the output, or maybe parts of the input and output, are actually kept as secrets from the verifier. And then the proof shouldn't reveal anything about the things that the prover doesn't want to necessarily reveal. So zero knowledge, I'm not going to focus too much on zero knowledge, but this is all within the realm of zero knowledge proofs. So it's worthwhile mentioning that. So Lurk is, if we wanted to just end it there, you could kind of just generate some sort of like circuit that would describe the semantics of the CEK machine and then unroll it a certain amount of times, and you would be able to prove things about Lurk execution. But that's not actually what's done in practice. And so now I want to talk about not verifiable computation, but incrementally verifiable computation. And so if we have f, some function that we want to repeatedly apply, so thinking in our heads something like the CEK abstract machine, or maybe something more concretely like, say, the like a RISC-V assembly machine. So a machine that has some very simple set of rules that are deterministically applied at every step. And you just basically, in order to do your computation, just repeat this function over and over and over again. Then, how would you go about doing this? And so what you could do, like I said, you could unroll that function a bunch, and then the prover's work would just be take all of this unrolled function and then provide a big proof about it. This is roughly equivalent to just providing a separate proof for each individual function application. So the top result, so this is kind of like the duality of how much work does the prover have to do versus how much work does the verifier have to do. So in the top step, the verifier only has to verify a single proof, but because this function is so big, it's, a single function unrolled a certain amount of time, the amount of work that the prover has to do is a lot. And so generating the proof here would be very costly. And but on the other hand, the verifier work would be a lot less. Here, generating the proof would also be very costly for the prover because they have to generate a proof for each individual application of the function f. And then the verifier cost would also be costly because they have to verify every single individual proof. And so the idea behind incrementally verifiable computation is you want to reduce the amount of work that the verifier has to do by being a little bit more clever. And the idea is because V is just the verifier function, the function that takes in a proof and spits out 0, 1, because the verifier function is just some, NP function or an NP relation, you can arithmetize it as well. And so now I'm going to increase the prover's work at any individual step. And instead of just taking in an input z and applying the function to it, I'm going to take in the input z, apply the function to it, and then also verifiably, or provably verify the last proof. And so here, if I, as a verifier, receive pi out, what do I believe? What I believe is I've taken this function and I've applied taken this input z in, and I've applied f to it, and I've gotten z out. And also, I've received the proof from the previous step of the execution, and I verified it, and I believe that proof. And so now you can sort of inductively take a step back. And so now, because I believe the proof pi in, I should believe that it was generated correctly from the previous step of the execution. And so, and so we can sort of piece this all together, and this is the notion of a recursive snark. So snark is succinct, non-interactive argument of knowledge, essentially this kind of zero knowledge stuff that I've been describing. But at every step, the verifier or this verifier circuit is going to verify the previous proof, and we're going to provide a proof for the whole of evaluating f and verifying the previous proof. And so at the very end, the very last step, the verifier, when he receives a proof, they're going to take the proof, verify it, and if they do verify it, then you can inductively go all the way back to the beginning and say, oh, I'm confident that this function was calculated correctly at every single step. Is there any? Okay, sorry. I have chat open. So if you do have questions, I guess I didn't say this earlier, but if you have questions, definitely stop me at any point. Or you can just leave the questions to the end, I guess. But definitely don't feel
Use
like you
this as
shouldn't ask questions.
appreciation.
Yeah, just appreciation. Yeah, no, this is really cool. But we're not done. So this is cool, but there's kind of like a little bit of a problem about even the simplest snarks. The verifier circuit ends up being very large. It's about 1 million constraints. And to put that into context, calculating a SHA-256 hash, sort of the most efficient implementation of that is roughly like 40 something thousand constraints. So and then so that's calculating a SHA-256 hash. SHA-256 turns out to be a very bad hash function for zero knowledge proofs. Actually, any hash function that you're probably familiar with, like Keccak or Blake or SHA-2, SHA-2, SHA-3, these are all kind of like not great hashes for cryptography or for zero knowledge proofs because they're defined in terms of bit operations, and bit operations are costly to implement in terms of finite fields. As you saw, in order to have a single bit, I need to have a single constraint. So anytime you have a bit, you have a constraint, and that kind of really adds up. There are more. There are these things called algebraic hash functions, so hash functions that are suitable for zero knowledge proofs. So there's examples like Poseidon, Poseidon 2, Grostel. There's a lot of hash functions that are more suitable. And there, the constraints for hash functions are closer to like 200, 300 constraints per hash. And so compared to like 1 million constraints for a verifier circuit, that's actually really big. So you don't necessarily want to be verifying the full proof at every given step. So there needs to be a better way. And there is a better way. So there's this notion of folding. So I should say actually a little bit taking a step back. Incrementally verifiable computation was introduced, I think in like 2006, 2007 or something in a paper by Valent, where it was kind of introduced out of the context of cryptography and zero knowledge proofs. But an actual like useful implementation of IVC was introduced in 2022 by Srinath Sethi at Microsoft and collaborators on the paper, where they use this notion of folding. And what folding does is you introduce this additional uppercase pi proof, and at every given step, the folding, you sort of fold in a proof into this bigger proof. And at every step, you fold in this proof into a bigger proof. And so pi itself doesn't get bigger over each step, but you're kind of cryptographically folding it in. And so if you believe this bigger proof pi, then you should believe that this folding verifier was done correctly. And that, this little pi verifies correctly, and then that it was folded in correctly into the verifier V, or into this big uppercase pi, like this. And so then at the very end, the verifier only has to do the final step of folding and verify this single proof pi. And in the actual implementation of folding called Nova, and later improved in Supernova and Hypernova, the cost of verifying this uppercase pi is roughly equivalent to the cost of verifying a lowercase pi. So in some sense, what you're doing is you're amortizing the cost of verification of many different steps in your recursive calculation into the verification of a single step at the very end. And the V here, I should note, is the folding verifier. So compared to above, where the verifier was the full snark verifier, a very costly operation, down here, the folding verifier is actually a lot more suitable to do in circuit. And just for context, the Nova folding verifier is roughly like 20,000 constraints. So orders of magnitude less expensive than verifying a full snark. And so this work on folding basically unlocked the ability to do incrementally verifiable computation in the context of zero knowledge proofs. And that's this Nova folding system is the underlying cryptographic system that Lurk uses in its execution. So bringing this all back to Lurk, let's kind of put all these things together. So Lurk, the Lurk data are just very simply S expressions, and they're stored as unique content addressed hashes. Here, the hash function that's being used is one of these algebraic hash functions. In particular, it's the Poseidon hash function. And the idea is that if I have like a cons list AB, then it's stored as a unique pointer, a single field element, which is the hash of the concatenated hash of A with hash of B. And assuming the collision resistance of the Poseidon hash function, this is a unique content addressed value that you can associate to any S expression in Lurk. And then how does the execution happen? Well, you encode a single step of the CEK machine in terms of the circuit F. The Lurk circuit is roughly 10,000 constraints. It's very small, like it's tiny compared, it's even smaller than the folding circuit that you need to do at every step. So the Lurk circuit is very small, and it encodes a single step of the CEK machine. And so essentially it takes in the three pieces of data, the environment, or sorry, the expression that you're evaluating, the environment, and the continuation. All of these represented in terms of Lurk S expressions. So in particular as just basically three field elements. And it applies non-deterministically, it deterministically applies the CEK machine, and it spits out three new field elements: the new expression, the new environment, and the new continuation. And just does this over and over and over again. And that's essentially how Lurk is implemented. And you'll notice here that one kind of benefit of this Lurk way of doing evaluations is for if-then else's, Lurk doesn't have to evaluate all different branches of an if-then else. If you apply the Lurk continuation on the value of the if, the conditional. If it's a true conditional, then you'll end up going in a single branch, and that's going to be the next step of the Lurk execution. And if it's false, then you'll go to the else branch, and that'll be the next step of the Lurk execution. So this kind of fixes some of the issues that are associated with the flat circuits that you get for general verifiable computation. Digging a little bit deeper, so how could you, for example, calculate the car of an S expression A dot B? So the idea is that you first do the execution out of circuit. You've essentially evaluated the Lurk function, or you've essentially evaluated the Lurk expression all the way to the very end, and you have this store of all the various content addressed hashes that have appeared throughout the execution. And so, for example, if at some point I need to provably evaluate car of A dot B, then what you'll do is what the prover does rather is they'll non-deterministically supply the hash of A, and then, the hash of A and B. And then inside the circuit, all you have to check is, okay, well, is hash of A, hash of B hashed together equal to the pointer of this cons list here? And so that's kind of how you do these executions. You have to non-deterministically supply the preimages of all these hash functions. And again, assuming that the hash function is collision resistant, it should be difficult for a cheating prover to get by. So verifiable computation is cool. Lurk is really cool, but so what are some things that this unlocks? And so non-determinism, I've mentioned a number of times up until this point, but a clever prover can really reduce the amount of work they have to do if they can non-deterministically supply values in the appropriate places. So you can really implement super efficient provers by leveraging non-determinism. Another really cool thing that verifiable computation unlocks is memoization. So once a function has been evaluated and the proof pi has been provided, then that computation never has to be repeated again. And you don't have to worry about a cheating prover or a cheating, execution ever, working and giving you the wrong value. Once you've received that value once, you never have to calculate that thing again, because the proof can just always be repeatedly verified. And then the last step, or the last thing I want to mention is out of order execution. So what this idea of memoization together with out of order execution kind of unlocks an idea of structuring the computations in an appropriate way that can leverage memoization the most efficiently. So what you would want to do is maybe you could like look at the graph of your execution and find common subgraphs for those executions. And then once you do once you do a computation and do an evaluation for a single graph, then anytime that same subgraph appears in the computation that you're doing, you can use the memoized result already. And so this out of order execution is not useful if you're not proving the execution of your function, just because there's probably some overhead that it takes to find the most appropriate order of execution that you would want outside of the provable context. But if you're really proving, and the overhead for proving is roughly like 1000x over the actual cost of execution, then if you're proving, then it really does pay to take all of these shortcuts and use all of the efficiency that you can gain via out of order execution. So then kind of putting it all together, Lurk allows you to, write down some function in a high level language. And then once you've done all of the computation that you're interested in, you can call this prove meta command, and it'll generate a succinctly verifiable proof. This proof is portable, so you can send this proof to anyone who has the Lurk binary on their computer, and they can inspect the proof to see what the proof is actually claiming, and they can verify the proof, and the Lurk verifier will, which is roughly just the cryptographic verifier of Nova, will just check, does this proof check out? And if it does, then you can be assured that the calculation that you've evaluated or that's been provided to you has been evaluated correctly. And there's a lot more to Lurk that I haven't mentioned, but there's non-uniform IBC, which we've implemented. There's this notion, there's notions of commitments, functional commitments, chain functional commitments. There's a lot of interesting optimizations that were put into place to really get the Lurk circuit this small. Some of them are things that we call internally like slot allocation for hashes and efficient environment lookups. So talking a little bit about environment lookups, if your environment is just a cons list of an association list of a symbol to a value, then walking through that cons list, each step is a very costly operation. So if I have some symbol that I need to dereference that's very deep inside the list, it could be very costly to look up that value in the evaluation. So there's a lot of interesting optimizations that were done around environment lookups to make that less of a costly operation. And then there's probably more interesting things about Lurk that I'm just, not really thinking of at the moment, but maybe will come up in the course of the question and answer session. And so that's basically all I want to say. Here's some references. There's probably a lot more references that I can provide as they come up in the question and answers. And then finally, I think I will move to the demo. Just a really quick demo. I just want to show off that I'm not talking about any vaporware. This thing actually exists. So let me pull up my terminal. Okay, and I probably should make this bigger. And share new screen. Okay. All right. Hopefully that's readable. Is the text big enough to be read?
Yeah, looks good to me.
Okay, great. So yeah, so I can just go into the Lurk binary. So I'm in the REPL, so I can just start evaluating Lurk expressions plus 2 equals 4, as you would expect. There are some things that you wouldn't expect. So if I subtract 1 from 0, I'm getting some very large number here. It turns out that, like I said earlier, the functions or sort of all of the numbers that are appearing are basically field elements. And this is essentially kind of telling you what the modulus of the prime number is that I'm working over. So this is a very particular prime. It's used because there's like some cool cryptography there, but it's used because there's this notion of a cycle of elliptic curves, and we're using a particular cycle here, the BN254 cycle. And this is the modulus of the BN254 field. So I can give you some slightly more complicated expressions to evaluate. So let me pull it up so I don't have to fumble around with parentheses. I have them written down right here. Sample.lurk. Perfect. So kind of going back to the Fibonacci example. So I first define the core inductive step of Fibonacci, and now I have the Fibonacci function. And I can, like I said before, apply Fibonacci to 10, and I'll get 55 with 179 iterations, like I said above. And then I can run this prove command. And so here, it'll take a bit because I think I'm using power saver mode, actually. If I turn that off, it'd be a little bit faster. But proving is essentially now generating a proof that I've calculated fib of 10 and I've gotten 55. And so here, this proof key, I can take it. Let's copy and paste. Oh, actually, I want the quotes as well. So let's copy this proof key. And if I inspect the proof key, it should tell me that this is a proof that taking as input fib of 10, the output is 55. And then if I verify this proof key, verification should be a lot faster, but the proof checks out. So it's yeah, so the proof works out. So what is this proof key really? So the proof key is so the proof key is really pointing to a file that's generated, this proof file. I can actually show you roughly how big it is. I think it's like 16 kilobytes. Yeah, so the proofs folder is like 16 kilobyte or 32 kilobytes. So the proofs are relatively small. They're still pretty big on, in the grand scheme of things. But the proofs are pretty small. And I mean, they're basically binary files. And so let me sort of like mess up one of the this proof, and let me just like change this I don't know, this B to a C. I don't know. It's some binary file. I've changed the proof. And now if I go back and I try to verify this proof, I've changed some parameter somewhere, and the proof is no longer going to verify. So that's a good show, a good test to show that we're not just always saying that the proof is verifying.
It would be really fun if that demo failed, because that would be
if it didn't fail, then there would be like some weird cryptographic thing that just happened, and it would probably be worth looking into.
Yes.
But the fact that it did fail to verify is a good sign. And then, like I said, so there's I mean, if you go into the repository, there's a whole demo folder, and you'll see there's a lot of interesting demos. And so there's a whole bank demo, and you can see kind of an interesting example where we use a lot of the features that I haven't described about Lurk, called functional commitments and chain functional commitments, to basically implement a very simple but like essentially fully featured bank which has zero knowledge and has all the privacy guarantees that you would expect from a bank, but implemented in Lurk. But I think that's basically all I really wanted to say. You should definitely check out Lurk RS if you want to play around with it. We have a really active Zulip channel for the Argument Computer Corporation if you want to pop in there and ask any questions if things come up through your explorations. But I guess I went a little bit longer than I expected, but if you guys just want to throw any questions at me, I'm happy to stick around and answer questions.
Matej, this was great. Thank you so much. And
yeah, thanks. I think I'll stop sharing.
Maybe I'll get us started, and then I think we'll have questions from other people. Can you just tell us like what some use cases are that you've encountered in the wild? I mean, presumably you guys have customers, right? Since you've gone through at least one round of venture funding, and they're going to ask who's paying for this. So,
Yeah.
who's paying for this? What sort of use cases are you seeing? Are any of them surprising, or is it just like a bunch of smart contracts, which is fine too? But yeah, I'm just kind of curious, like where this is actually being used in the wild.
Yeah, so I would say at this point you see a lot of applications in smart contracts and blockchain applications. In principle, because it's just a completely, fully fledged language where you can generate zero knowledge proofs of execution, it should in principle be useful for anyone. And we're really happy when people start providing us interesting examples of applications. So we've had people, write like JSON parsers in Lurk. And we've had people who, on the other hand, we've had people who have been implementing like zero knowledge blockchains, like succinct blockchains, and using Lurk as like a smart contract language, and uh, unlocking some sort of like um, succinctly verifiable proofs on chain, which is an interesting application. Um, Recently there's been a lot of work internally where we've been doing work on like light clients for blockchains. But yeah, I mean, if people want to start using Lurk and if they see an application where they need to start generating verifiable computable code, then like Lurk, I think is like one of the best examples of, or best places where you can use it. Like so Lurk now is great, but like I don't want to spoil too much, but like Lurk in like 2 or 3 weeks when we can finally start talking about things is even going to be better. So it's a great language to use, and it'll only be getting better.
Well, we'll have to have you back to tell us about the improvements.
All right.
Sounds good. So a follow-on question to what Max was asking is that if we look to sort of like verification in this way seems new, and it's really cool that there's a lot of effort going into making a good language where this is natural to use. Because a lot of these tools don't have this kind of usability that you did in a demo. But I guess one question I have is about the limitations of some of these things. Because, for instance, we have formal methods, we have theorem provers, we have all sorts of things, and people try to do some audacious projects like let's verify the Linux kernel and stuff, and then
Mhm.
it fails due to side channels and bad constraints and things. But it does work really well for network protocols. For instance, like we're talking about Web3 type things, blockchain stuff. Max actually did a bunch of formal methods to find some issues with a particular protocol in Ethereum called Gossip Sub. But I'm guess so, yeah, as a dual to kind of the customer question, where it's like who's going to use this, what are scenarios where you think this is relevant, regardless of if someone's paying for it or not, and areas where it won't work? Because I'd imagine there are some types of computations that are just too expensive to verify. And when do you actually care enough to do a slowdown that lets you verify something, right? It's a
Yeah,
broad.
so bringing up like formal methods is actually really interesting, and like formal verification, because when I got hired at Yatima at the time and then turned to Lurk Lab and now it's Argument, I was originally working on like formal verification of like some cryptographic stuff. Like I didn't know any cryptography like 2 years ago, or maybe 2 years ago I was starting to learn a little bit about cryptography. But one interesting application is so the theorem prover of choice that I was using at the time was Lean 4, and one of our first kind of projects and things that we were able to develop was the Yatima kernel. And so this was a compiler that took Lean 4 and spit out Lurk. And so what it essentially allowed us to do was type check Lean expressions or type check Lean environments and generate zero knowledge proofs for these type checked objects. And so essentially, like, I mean, I don't know how much about Lean you're familiar with, but there's a large library of formalized mathematics called MathLib in Lean. It's probably like 2 million lines of code at this point, maybe like 1.5 million. And it's everything from very basic set theory all the way to super advanced algebraic geometry. And it takes on like a pretty beefy machine, roughly like an hour, maybe 2 hours to build all of MathLib and like build and type check and et cetera. But if one were to be able to take mathlib, type check it using this zero knowledge type checker that generates like a zero knowledge proof out in the end, then you would be able to succinctly verify all of mathlib, all of the type checking of mathlib in, however long it takes to verify a Lurk proof, which is like roughly on the order of a few seconds. And so mathlib is an interesting example from like a theoretical perspective, but there's also other things that you would want to verify. So for example, if I have some smart contract and I want to be able to verify that the smart contract is correct, then I would do some formal methods. I would do some formal verification on the smart contract, provide a zero knowledge proof of type checking for these formally verified proofs that I'm generating. And I could even put these things on chain. And so I would be able to on chain verify the smart contract that I'm using is correct, or has, the specification that I expect from it. And this, without having, the end user to download whatever zero knowledge or whatever theorem prover and rebuild and re-type check everything from scratch. So this idea of like the confluence of proofs in the sense of like formal verifiable proofs and proofs in the sense of like zero knowledge proofs is kind of like at the heart of argument. And it's like from the very beginning, one of the first things and one of the first applications we've been thinking about. And so, yeah, I mean, Lurk as it stands now is maybe a little bit too slow to do some of the things, but it's really, with the improvements that we're implementing right now, it's really getting close to like a feasible task of like formally verifying like massive lean 4 environments and doing some like really cool things. And once you can do that, like you unlock a ton of interesting applications like that I can't even imagine.
Fascinating. Thank you.
Yeah. So I got a question. So could you in principle do the same thing for Clang to generate proofs a binary comes from some source code? Yeah, so if you could compile Clang to Lurk or some other verifiable language, then you would and you ran Clang on some source code, then the proof output would basically say this function, this Clang compiler that I've fed into it, takes in as input this text source file, spits out this binary output file, and I can verifiably prove to you that I've calculated this output binary correctly. And so, yeah, so in principle, yeah, that would definitely be possible. I mean, if verifying mathlib is kind of at the edge of what's possible, compiling Clang to Lurk is kind of getting a little bit further, but
you might just be proving that, like, yes, I successfully installed the supply chain attack from my, third-party package that I used.
Yeah.
Or something.
Yeah, that's a good point. Yeah. But no, that is interesting. Like having a, say you had even something like I forget the name of it, but there's these like verified compilers. They may not do all of the interesting optimizations that like Clang or GCC can do, but they're out there, and they match a certain specification, like they've been formalized in Coq or whatever. And if you could compile those to Lurk, then you would be sure that your output binary has been compiled correctly, and post that proof up together with the binary, and it'll be even more of assurance than just like some SHA-2 hash that you would some checksum that you would do when you download. But that's also a very interesting application.
Is Lurk ready for quantum computers? Can you just swap out your hash function for a beefier one if you need to? How does that work?
Yeah, so not quite. So some of the security of Lurk comes from the hash function. Hashes aren't, breaking a hash function using quantum computers there is a slight speed up for hashes, but really most of the security for Lurk as it stands now comes from the discrete logarithm problem on elliptic curves. So actually Lurk RS, as I've shown you in my REPL, would not withstand quantum computers. The new version of Lurk that we're working on has changed the underlying cryptography from discrete logarithm-based cryptography to post-quantum hash functions. And so the new version that we're working on not only is much faster, but is actually quantum resistant as well.
By the way, do you want me to
So
like wait before releasing this video if
no,
that's
no, no, that's well known. Yeah, people we've been yeah, there's been rumbles. I mean, like, I don't know how into the ZK community people in this call are, but there's kind of like two camps generally. There's the people on the snark side. Snarks generally use like discrete logarithm problems, elliptic curves, like you know, interesting algebraic objects, but things that aren't post-quantum secure. And then there's the other hand, the Stark type provers, and so those are generally hash based, and the security comes from the pre-image resistance for hash functions. And essentially, the new version of Lurk that we're working on is based off of pre-image resistant hash functions, and so in principle should be post-quantum secure, as long as we make the hash functions beefy enough to avoid like the quadratic speedup you get from some of the quantum algorithms, from Grover's algorithm.
Is there a theoretical lower bound to how close these circuits can get to the just regular compute?
That's a good question. I don't think so, because, well, I mean, there may be. I don't think it's been written down. And in practice, over the last, since like 2017, when these things have really been put into practice, the speed ups have just gotten more and more, and they've compounded on top of each other. And so now, we're verifying things much faster than we were in the past. And the fun example of like running Doom on a calculator, or running Doom on your smart fridge or whatever. There's a cool demo by a team in the ZK space. Their name is RISC-0, and so they have a RISC-V virtual machine that can generate zero knowledge proofs of execution. And I think they're running at roughly like a megahertz provably, or something like that. And that's getting close. And they were actually able to do a little bit of a demo on Twitter where they were able to give a proof of like running through the first level of Doom or something like that, which was really cool. And so it's getting close, and thinking about like 2 years ago or whatever, that was so far from anything that we would have expected in terms of performance. And so it's just getting closer and closer to just like raw execution. But there's always going to be a little bit of an overhead, because you're always going to have to generate the proofs. But the protocols for proofs have just gotten more and more efficient over time.
That's super cool. Thanks.
Yeah.
Sorry if this is outside your purview and you're like, I don't know, that's fine. But like, are we seeing similar speedups with homomorphic encryption and that whole world? Are they also getting closer and closer to like being able to do real compute at normal speeds?
Yeah, there's a lot of speedups there too. I don't know a ton about homomorphic encryption, but I know enough about it because there's a lot of like excitement in terms of like combining FHE with zero knowledge proofs.
Right.
And I know, there's the overhead that FHE has, but then there's the additional overhead of ZK on top of that. So combining ZK and FHE is like way far out.
Okay.
But there's like rumblings that people are confident that maybe in like 5 or so years there's going to be enough improvements generated that like you may be able to do some like very trivial FHE plus ZK stuff. And if you're able to do that, that must mean that some new breakthroughs have happened in FHE. So I don't know too much about FHE, but I know that there are improvements constantly ongoing in there. But they similarly have like a similar structure where you're taking a computation and you're sort of arithmetizing it, you're using like garbled circuits or whatever types of FHE primitives, and so there's like that overhead there, and the proving systems that you have are just getting more efficient in FHE as well.
I was curious about the folding stuff you
Mhm.
mentioned. I felt like leading up to that part in the presentation, like I could track like something is NP hard, you give a trace, you prove you've done it, but it's hard to get there.
Mhm.
Like the folding part though, I like don't really have any intuition about. And I was wondering if they're like if you know of an intuitive way to describe how that folding happens.
Yeah, um it may be worth mentioning a little bit about. So I know folding in the context of Nova, and so the Nova folding scheme uses as its arithmetization is R1CS. So let me take a step back and say, what is R1CS? So it's a so it's an so it's an arithmetization where the constraints are essentially products of linear polynomials. So like any given constraint that I can write down will be something like linear polynomial times linear polynomial equals some other linear polynomial. And these are linear polynomials in the variables that I'm allocating in my circuit. And you can rewrite this as basically like a matrix equation, saying like if I take z as my vector of inputs and witness variables, basically all the variables that appear in my circuit, then it's az. So then I'll have basically three matrices, A, B, and C, and the equation that I'm sort of like trying to prove I'm able to satisfy is AZ circle product BZ equals CZ. So circle product is this Hadamard product. It's not super important, but it's a matrix equation. And so why do I mention this? So I mention this because the basic idea behind folding is actually very simple. So this folded proof, pi, this big pi, is essentially like a random linear combination of the previous big pi with the little pi. So it's like the verifier is going to generate some random number, send it over to the prover, and the prover is going to take a random linear combination of the accumulator together with this smaller the individual proof, and then because the verifier is generating this randomness, not the prover. So if the prover could generate the randomness, they could cheat. I'm gonna, generate this randomness in such a way so that, I could generate the randomness to be 0. And I'm all I have to do is verify like this trivial proof at the very end, and it would just fool the prover. But because it's the prover, or sorry, because it's the verifier that's generating this randomness, the prover kind of doesn't get to like look ahead, doesn't get to do any of these tricks. And what they're gonna have to do is just kind of go along with the flow if they want to generate a recursive proof that the verifier will be happy with. And so essentially what you do is you take a random linear combination using a verifier randomness of these two proofs, and then you spit out this new accumulator at the end.
And the
And
idea being that it's been like given a I keep going. We're getting close here.
yeah, well, and so then I'll just say like if this random linear combination satisfies this matrix equation, roughly because of linearity, each individual summand in that random linear combination has to satisfy that matrix equation as well. So there's a little bit of a lie there, just because the matrix equation I described is not actually linear, it's quadratic. So you have to be a little bit trickier. You have to keep track of cross terms, and so it's not totally obvious how folding works, but the rough idea is essentially take a random linear combination of the two proofs, and you get a single proof out in the end, and that single proof is what you verify.
Matej, this has been awesome. Thank you so much for joining us.
Yeah.
We've taken a solid hour of your time on a Saturday, and
Yeah.
appreciate that you would come talk to us. If people want to get in touch, if they want to try Lurk, if they're curious about, I don't know, I mean, you may get inbound on job openings at Lurk for all I know. Like where should they go? Should they email you? What should they join this Zoo?
we have a Zulip. So let me, before I go, Zulip argument computer dot org. Is that what we are? I want to make sure I get the right
Okay.
Zulip.
Once you send it, I'll put it in our Slack so that people see it. So they don't have to like hurry to copy paste before we close the Zoom. But
Yeah. I just want to, yeah. Oh, sorry, it's .xyz.
okay.
Yes, okay. This is our Zulip channel. You guys should definitely pop on.
Awesome.
Ask any questions in like the Lurk substream or anything. Tell everyone that Matej sent you. We're all very friendly there. So definitely come by and say hi.
Perfect. Okay, I've put it in the channel so people have it on Slack. Yeah, thank you so much. It was super fun, and we'll definitely have you back when you've got a new version of Lurk to tell us about, because I think it's
all right. Cool. Yeah, there's a lot of cool things that are brewing right now. So I'll
awesome.
happy to talk about those.
Okay, sounds good. Adios.
Cool. See you later. Bye.